Well, thank you very much. It's wonderful to be here with you all, and it's wonderful to be here with you, Martine. Thank you very much.
My pleasure, Jane.
So you have lived an extraordinary life, such a brilliant mind, as you'll see here in this next 45 minutes. It's not often that a person has published books in the following categories: satellite communications, gender differences, genetic engineering, organ transplantation, and Middle East peace. You were born Martine Rothblatt. You and your wife, Bina, have been married 30 plus years. Tell us about your family.
Bina's been my partner and soulmate for 33, 34 years. Just amazing person, definitely my best friend. We've had 4 children together: Eli, Sonny, Gabriel, and Genesis. Genesis, our youngest daughter, is the one that developed primary or idiopathic form of pulmonary arterial hypertension in the early 1990s. We now have 4 grandchildren, and we've really had a great life. I know that the transgender transition has resulted in most transgendered people having very damaged family relationships with rejection, either from spouses or parents or children, unemployability. And I definitely say I just feel incredibly blessed that the love of my life loves me as I am. All 4 of our children said, you know, fine, go forward with the transition, and we're best of friends to this date. My parents and Bina's parents have been accepting, and my colleagues in the satellite communications and healthcare industries have been accepting. So I just feel very blessed and fortunate.
So this is a distinguished medical group here today. But to give some perspective on your accomplishments, I want to go back a little bit. It was mentioned that you started SIRIUS XM radio. Tell us how that came about and how you made that invention.
Sure. I'd been very active in the satellite communications field, as was kindly referenced in my introduction. And I kept asking the question. One of my big motivations is to question authority. So I kept questioning the authorities on why did satellite dishes have to be so large. Many in the audience may have seen the satellite dishes at a cable television location where they're big dishes, and even the DirecTV satellite dishes would obviously be too big to be put on a car. And I learned that the reason why was that the signal from the satellites were so weak that it required a large collecting area to collect the energy from the satellite signal. So I got very deep into the satellite communications technology in terms of what could be done to make a satellite signal powerful enough that it could be received by just a small flat section of a parabolic dish, a small flat section that could be embedded into an automobile. And it turned out it would take a satellite 3 times more powerful than any satellite that had ever been launched. So I undertook to work with aerospace manufacturers to create that kind of a satellite, rocket launch manufacturers to create a shroud large enough to carry that size of satellite. And then the biggest effort was with the Federal Communications Commission to create a radio frequency band that could be used for that type of satellite communications. Everybody thought it was really impossible, Jane. Every step of the way, you couldn't make a satellite powerful enough, couldn't make a rocket big enough. There weren't any radio frequencies left. Even if there were, nobody would want to pay for radio. AM and FM is free. Even if people would pay for it, the first day there'd be only a handful of people. How could you support it? Every objection in the world. And today, it's amazing to me that there are 30 million subscribers to Sirius XM in the US, and more people really express appreciation to me for Howard Stern than do for the medicines that I've created.
So let's get to that.
Okay.
Here you'd created Sirius XM. You had plenty of money. You could have, gone on vacation for the rest of your life, but then your 4th child got sick, your daughter Genesis. What happened?
So Genesis, we were on a family ski vacation, and she was at pretty high altitude. She was unable to feel well enough to go out skiing. We thought she just was sick. As soon as we got home, she never got any better. She began to be out of breath or dyspneic with any amount of exercise. Her lips began to turn blue. Of course, all along the way, we're taking her to her pediatrician over and over. Maybe it's the flu, maybe it's a stomach ache. I mean, the problem with pulmonary hypertension is it's really a diagnosis of exclusion. And in fact, to this day, probably close to half the people who develop pulmonary hypertension die without it ever being accurately diagnosed. And it used to be much worse. It used to be probably like 95% of the people would die before it could be diagnosed. It progresses very rapidly without medication. There's mean survival. It's only 2 years from diagnosis. So it was a grim situation. We spent all of our time at Children's National Medical Center in Washington, D.C. The head of pediatric cardiology told us openly that all of his patients with the disease died. And then finally, when spending night after night at the hospital, I just began to go to the library and to read every single article that I could read on pulmonary hypertension. There was an article, there was a bunch of references. I would go and look up all the references, read all of them until I had got to a point of diminishing returns. And in all of that effort, Jane, I found one tiny article out of hundreds that reported on the test of a molecule for congestive heart disease that nevertheless was a pulmonary selective vasodilator, meaning that it dilated the pulmonary vasculature, but did not dilate the rest of the body's blood vessels, which was important because people with this condition, they have normal systemic pressures. So I like a light bulb went off in my head that maybe, just maybe, I could get the company to develop this medicine and that could save Genesis.
So what happened?
They weren't interested in developing it. The company was Glaxo Wellcome, now SmithKline Glaxo. It originally was the Burroughs Wellcome Company. And they said that the drug was being developed for congestive heart failure. It was not useful for that. And so they were locked up in the freezer. And I said, well, how about if I give you money to develop it? They said, you can't give us enough money. We're in business to produce blockbuster drugs, which are drugs that are going to create over $1 billion in revenue. And the last we checked, there were only 3,000 patients in the United States with primary pulmonary hypertension. We're sorry your daughter is one of them, but we could never make $1 billion from 3,000 patients, so we won't develop it.
So how did you use your expertise in the satellite communications company to find a cure for your daughter?
Well, I wish it was that simple that I could have promised them a one-on-one with Howard Stern or something, but no. The problem was that I did learn by being rejected so many times in satellite communications to always ask people why. I'm a little bit like that 7-year-old who keeps saying, why? So when they would say, when the Glaxo Wellcome said, we're not going to develop it, and I said, why? We can't make $1 billion. I said, would you license it to me? And I could do it on my own. And they said no. And I said, why not? They said, you don't know anything about drug development. It would be abnormal for us to license a molecule to a satellite communications expert. So I said, well, what if I had a team of drug developers who were expert in this area? They said, well, what if pigs had wings? Maybe they could fly, come back when that's the case. So that actually, to me, for a lot of people I know, it might have been depressing, but for me, that was like, wow. Now that little bit of light got a little bit brighter.
That was a challenge.
It was a challenge, and I do like challenges. So I did find the experts in this field of drug development. I offered to start a company and give them founding shares in the company to pay their salary. They knew the Nobel laureate, Sir John Vane, who had won a Nobel Prize for developing the type of medicines that this drug, this molecule was in that class of medicines, prostacyclin analogs, as well as discovering the mechanism between COX-2 inhibitors like Celebrex and whatnot. And I flew to the UK to meet John Vane. I told him my story, and it turned out that of the whole story, he was absolutely fascinated with the fact that one of my satellite communications companies tracked elephant locations by satellite. And he asked me to show him pictures of it, and I got on a computer screen, and he saw where you could track the elephants. He loved that, and he said, "Okay, Martine, I'll do whatever I can to help you." It's true.
So you wrote a check to Glaxo for $25,000 in exchange for, let's see, 10% of the revenues?
In exchange for the assignment of all the intellectual property to this molecule, the right to develop it worldwide, and I gave them both the $25,000 and 10% of any revenues we would earn from it.
Okay, and then they gave you the medicine?
Well, it was very important to them that I had hired people who used to work at Glaxo Wellcome, actually at Burroughs Wellcome, who knew this field, that Sir John Vane was now listed by me as the chairman of my scientific advisory board. And even then, in the real world, it's not that simple because no one person can actually get a medicine out of a big pharma company. But it turned out the head of R&D said, "I will go to bat for you." He said, "I need to get about 20 people at this pharmaceutical company to agree to license out a medicine." That took a few months. He did it. And then at the end of the day, we had the exclusive rights to develop what was just a molecule. It was a patent on a piece of paper, a little tiny bit of powder that would not have been safe to give to any person. Certainly no clinical development in pulmonary hypertension, not even a smallest study in pulmonary hypertension. We had that little thing and a right to try to develop it. That's all we had.
I see.
And by that time, our daughter was like about half the time in the intensive care ward and always on a monitor. But I ran like the devil, Jane, and got everybody working very hard. Ultimately, we found a manufacturer for the medicine, which took a 23-step chemical synthesis. I can't explain to you how difficult it was just to find a way to synthesize this medicine. Develop the clinical trial. Find this medicine has a half-life of only 2 hours. People with pulmonary hypertension, they have the disease because their body does not produce enough of a natural molecule called prostacyclin. Prostacyclin has a half-life of only a couple minutes. So your cells constantly produce it and use it, produce it and use it. Keeps your blood vessels dilated. It prevents platelets from sticking. So to make a copy of that molecule, an analog that lasted 2 hours is a great accomplishment, but it still means you can't take a pill every 2 hours. I had to figure out a way to deliver a medicine 24 hours a day, 365 days a year, without being in a hospital, because I didn't want Genesis to live in a hospital. In the 90s, nobody had ever done that. So we developed a whole delivery method. Long and short of it, in 2002, this medicine was approved by the FDA. And because of this medicine and subsequent versions that we and others have developed, today, instead of there being 3,000 people with pulmonary hypertension, there's almost 40,000 people in America with pulmonary hypertension. And some people say, well, is that good or bad? I say, no, that's like really, really good because all those other people would have been dead. And instead of the mean survival being a couple years, it's 10 years. And these are tens of thousands of people alive today because of the medicines we've created.
It's remarkable. Remarkable.
Thank you.
So you put this drug on the market in a brilliant way. Explain to us what you did and the thinking behind it.
So Glaxo Wellcome was correct that they could not figure a way to make $1 billion out of 3,000 people. What they had not really thought through is that if the medicine worked in pulmonary hypertension, which they had really no reason to believe it would, now that I'm in the pharmaceutical company, I realize how skeptical and cynical drug companies are about, small n's and subgroups analyzed after the fact. So there's a lot of room and justifiable room for cynicism. But I envisioned that there would in fact be tens of thousands of people taking the medicine, taking it for longer and longer periods of time. And I just did a mathematical calculation of how much would I have to charge for the medicine in order to repay all of the development costs and to keep developing better and better forms of the medicine, ultimately a cure. So I did the arithmetic, and to a round number, it came out to be $100,000 a patient a year. And I was shocked, because that's a lot of money. At that time, other than a few hemophilia drugs, no medicine cost anything close to $100,000 a year. So I said, okay, will anybody pay for this? And I pulled out my, at that time I had Blue Cross Blue Shield. I pulled out my Blue Cross insurance policy, and it says we'll pay for any medicine that's medically necessary, excluding cosmetic or lifestyle type of medicines. Well, clearly this medicine was medically necessary. It didn't say anything in there about a price cap. So I decided that we would announce the medicine as $100,000 a year, but anybody that did not have the money for the medicine would get the medicine for free. And I knew already that if this medicine didn't work, the only hope for a pulmonary hypertension patient was a lung transplant. My PhD thesis was in organ transplantation. I knew it cost around $300,000 for a lung transplant, so I said, if you're even within $300,000 of your lifetime cap, you'll get the medicine for free. And so we launched the medicine in this way, $100,000, but for free if you couldn't pay for it. From 2002 all the way up until now, we've never turned away one single person for inability to pay, including undocumented people here in the country anyway. And yet, the total sales of our medicine now, in all of its different forms, now is about $1.5 billion a year.
Wow.
The people at Glaxo Wellcome have told me that this was the best investment that they ever made.
I'm sure that's true.
Because they get like $100 million a year, year after year.
Yeah. And how's Genesis?
Genesis is very well. Thank you, Jane, for asking. She's a remarkable young lady. Obviously, I'm super proud of her, but she has chosen of her own free will to work in our company to help develop better medicines for her and other people. She's the director of telepresence in our company, which means that she manages all the digital screens, digital walls. We have 10 different offices and dozens of employees and collaborators throughout the country. So she keeps everybody on message with motivational messages, the latest clinical development information. She appears at Pulmonary Hypertension Association fundraisers. October 31st, she was at, believe it or not, a zombie PAH fundraiser. So she's out everywhere. The courage that she has to constantly be in front of people who are thinking in their head, you have a fatal illness, is just an immense inspiration to me and others.
What was most surprising to you about the journey of this medicine?
I would say that the FDA approved it. So I don't want to delve, too much in the weeds here, but this is a very knowledgeable group, obviously, and the FDA has a standard for approving medicines that they have to have a so-called p-value of less than 0.05, which I explain in layman's language. It means that based on a randomized, well-controlled trial, that the odds of the medicine working by chance, in other words, being effectively a placebo, is less than 5 out of 100, okay, if it's less than 0.05. So what does that mean if you do a clinical trial and the statistics are run and you have a p-value of 0.06? So it means a couple of things. Almost all the time, it will mean that your drug will not be approved by the FDA. Does it mean it doesn't work? Not at all. And it's a benefit of me coming to this field from the satellite communications, because I don't feel any reason to bow down to like a 0.05 p-value. It means that the chance of the medicine being a placebo are 6 out of 100, or a 0.07 p-value 7 out of 100 versus 5 out of 100. If you ask most people with a life-threatening disease, they'll say, give me the 7 out of 100 chance that it's a placebo. Chances are it works, you know? But it's not the FDA's rules, and I understand that they need to be a gatekeeper against ineffective medicines. But in reality, a p-value of 0.06 works. So our clinical trial for our first medicine, Remodulin, had a p-value of 0.06. And the FDA staff recommended for that reason that it not be approved. And I don't know if you could like empathize with the tremendous sense of like dread and exhaustion that I felt after pouring everything, leaping all these hurdles, and missing by like, you know, 1.05 to 0.06. But we had a tremendous friend in Bob Temple, the head of the FDA's Center for Drug Evaluation and Research. We had patients who had taken our medicine during the clinical trial, and they came up on stage and told their story, how it had transformed their entire life and allowed them to see milestones like weddings and stuff that they wouldn't have otherwise seen. So remember always that this is all about the patient. It's always all about the patient. And Bob Temple stood in front of his own staff, the whole FDA at the big FDA auditorium. Probably a number of you have been at that FDA auditorium over there in Rockville. And he said, we should not be slaves to p-values. And I thought that that was astonishing, given that A, Bob Temple is a biostatistician. B, that the whole FDA is pretty much devoted to biostatistics at the bottom line of it all. And the FDA advisory committee that they had convened voted like 5-3 in favor of approving Remodulin, our medicine. And since that time, it's become the preferred medicine chosen by thousands of doctors to treat pulmonary hypertension patients with a parenteral drug. It's used by thousands of patients. I meet them all the time. People who've gone on to be mayors of towns, graduate, get married, deliver babies. I mean, you name it. It obviously works. But for a difference between 0.05, 0.06, and some goodwill of a few people and some super brave patients, it all would have gone down the drain. That's what surprises me the most.
What will you have? Extraordinary story. I love this quote about you. Whether she's inventing satellite radio, developing life-saving drugs, or digitizing the human mind, Martine Rothblatt has a knack for turning visionary ideas into commonplace technology. I want to move past what we just talked about to your latest projects because they're so interesting. You teamed up with Craig Benter, who's the decoder of the human genome, and to genetically modify the pig genome. To try to create an unlimited supply of human organs. Tell us about this.
Sure, Jane. So here, too, I was really inspired by a family medical issue. My grandmother had required a heart valve replacement back in the 60s. And they gave her a porcine heart valve, and my parents explained all of this to me. And I was just fascinated, like, you know, why would you give like a pig heart valve to my grandmother? By the way, she was a very observant immigrant, a Jewish American immigrant from Russia. She was kosher. So like, you know, we could never eat like bacon or shrimp around her, but here she had like a pig inside her.
In her heart.
But she was very pragmatic, and I've actually subsequently found all religions are really very pragmatic when it comes to saving a human life. Judaism, Islam, Buddhism, they all are cool with xenotransplantation, the transplantation of animal organs into humans. And it was explained to me that the pig, by basically a fluke of nature, its organs are the closest size match to human organs and are able to be that are also able to be reproduced in quantity. So the pig valves are stripped of all living tissue. So it's just the form of a valve that she and others receive. There's no immunological reaction with the pig valve. But I began to think that, like, now that we've decoded the human genome, and we're at the cusp of gene editing, knocking genes in and out, that we can now take it the next step, and instead of just transplanting a human valve, we could transplant a whole organ in which we use not just the form, but the whole functioning organ. And instead of stripping off all the living cells, just strip off those antigenic molecules that create an immunological reaction with the human immune system. Craig Venter was very supportive of this project, as were other pioneers in the field like Tom Starzl, the father of liver transplantation, David Sachs right here in the Boston community. So together we have now created the largest herd of cloned pigs, which are now genetically modified with 6 genes that are either human or pig knockouts that would interfere with the human hematology or immunology. Our pigs in animal models, our pig hearts have now survived for over 2 years, our kidneys for over 6 months, our lungs for over a week. These are world records all across the board. And at the rate that we are progressing in terms of gene editing on the porcine genome, I'm confident that it will not take more than 8 or perhaps 9, maybe 10 genes at most, which is astonishing, out of the tens of thousands of genes that humans and pigs have. So it only takes like pretty much a couple handfuls to create a tolerable organ. And the other benefit of doing this, because all xeno transplantation procedures would be planned procedures planned ahead of time, there is also a time to somewhat chimerize the recipient's immune system so that they will be able to be already primed to not overly reject the remaining molecules on the organ that reside from all the genes we have not knocked out, and so that they'll be able to tolerate the porcine xenograft, hopefully with all immunosuppressants wind down within 6 months. David Sachs has already demonstrated been able to completely turn off all immunosuppressants after 6 months. And in this way, we can create an unlimited supply of transplantable organs for everybody.
So it's not just long-lasting bodies that you're interested in, it's long-lasting minds. And this is such an interesting piece of who you are and what you see on the horizon. You say we'll soon be able to preserve the content of our brains. Tell us about BINA 48.
So BINA 48 is kind of an example of big data. It was a fantastic panel that preceded me, and I salute the conference for bringing big data and medicine together in this way. But we are already storing unprecedented amounts of our mind in big data. All of our e-commerce activities, our social media activities, the digital surveillance of us as we come and go, certainly our medical records to an ever greater extent, are all being digitized outside of our bodies and stored in one or another cloud. At the same time of all of this digitization of our mind's contents, the hottest area of software development is, again, as mentioned in the panel before us, is on the analytical side. All the data in the world is useless without analysis. So at the same time that people are doing bioinformatic and bioanalytical analysis for medical purposes, other people are doing the same type of coding with regard to personality, cognition, and ultimately the trappings of what appear to us to be consciousness. The fact that applications such as Siri and the analogs of that for Google and Microsoft are so popular, different companies are all trying to out-Siri Siri. There's a whole maker movement of people creating their own forms of digital doppelgangers, and there's an open source software system where hackers anywhere in the world, China, India, Russia, US, Estonia, everywhere else, can work on elements of human cognition and human personality using this common open source software and store it available for everybody on the web. So the efforts to create what I call mindware, in essence, a consciousness operating system, are going to proceed extremely quickly. At the same time, big data is growing exponentially. And when those two things meet together, you then have something that is going to act like Jane and talk like Jane, recognize the people that Jane recognizes. Now, whether or not this, what I call in my book, Virtually Human, whether or not this mind clone of Jane actually is part of Jane or is not part of Jane, that's going to be an issue for philosophers, psychologists, and ultimately lawyers.
You actually have, but Bina is an actual structure. I mean, she actually does exist right now. And
yes.
You talk to her, and she talks back to you as if she was your wife.
Exactly, yeah. And so I decided to build a physical manifestation of this as a robot that people could visualize better. Bina, my wife, she agreed with this. She was excited about it. So Bina 48, as she is known, is sort of like, you know, a pre-alpha test version of this mind clone concept. And what I like best about Bina 48, and I know what Bina likes best about it, is all the young people who are getting inspired to get into software coding. And especially, I'd say, the young women and girls who are beginning to start coding in elementary school, junior high, and high school. Bina 48 is the biggest hit with the crowd, with this group called FIRST, for Inspiration and Recognition in Science and Technology, which is hundreds of thousands of students across the country competing every year to build robots. And Bina 48 is just a super cool robot.
Google it. You'll love it. You'll love it. It's really neat. I want to get some questions from the audience,
Sure.
but I also want to ask you briefly. Spoke for about 45 minutes in the green room and had just an incredible conversation. But you told me about the pediatric voucher program, and I just wanted you to tell this group briefly about United Therapeutics, your company, just receiving approval for the first ever neuroblastoma drug in the United States.
Yeah, it's very newsworthy. It happened just this year. That the FDA approved the first ever treatment for neuroblastoma, which is a medicine we call Unituxin. True to our roots, for the 2 years that it was under review by the FDA, we gave the medicine for free to all physicians throughout the country for treating patients with neuroblastoma. Fortunately, you know, we're in the age of Obamacare and Affordable Care Act. So people will not have problems having health insurance cover it now. But if anybody did, we would give it to the patients for free as well. Because we were the first ones to do this, the FDA gave us a voucher that was the result of some tremendous effort by advocates for pediatric rare diseases, specifically, I think, pediatric cancers, but other rare diseases, that they had successfully lobbied Congress to require the FDA to give a voucher that cut in half the time for the FDA to review a drug to the first three or four companies that developed a brand new medicine for pediatric oncology or other orphan condition, because Big Pharma was ignoring these. Well, I mean, this was true to my heart, because this is like Back to the Future, right? I mean, when I started with pulmonary hypertension, Big Pharma was ignoring us. And so I was really happy to do this. I actually did it, we did it before there was such a voucher program. And when we got the voucher finally, all kind of big companies were banging on our door saying, you know, we'll buy the voucher from you, we'll buy the voucher from you. We said okay, because we didn't really have a need to have a half-fast FDA approval. And we put it up for bid, and the highest bidder, I think, was AbbVie, $350 million.
Wow.
So I think that, a tremendous amount of credit goes, first of all, to the patient advocates who got the orphan voucher program through Congress. I know they were inspired by the kids with cancers and other rare diseases who are the bravest souls this planet has ever seen. And ultimately, I think it's proof of the adage that if you do the right thing, the money will take care of itself. I didn't start to make a medicine for money, but as was explained, it has produced a lot of money. We didn't do our neuroblastoma drug for a $350 million voucher, but has produced a lot of vouchers. So my advice to everybody is do the right thing, and the money will take care of itself.
It's amazing. Any questions from the audience? Any questions for Martine Rothblatt? Yes.
So your ideas are incredibly cutting edge, and I'm wondering, have you ever encountered an idea where maybe we could do that, but we shouldn't do that from an ethical perspective?
So I tend to look at things, more like on a continuum than in a black and white sort of way. So I would look at something like, if there's something that we could do, and that there was benefit from doing it, but we shouldn't do because it had bad consequences, then I would try to ask the question, is there a way that we could do it that maximizes the possibilities of good and minimizes the possibilities of harm? A classic example of that is recombinant DNA work. There is certainly a good reason not to modify viruses with, say, oncogenic genes. I think we'll all agree good reasons not to do that. And that point of view came into the minds of all the people in the recombinant DNA field back in its early years in the 1970s. So what was developed was a protocol that still rules the day for biotechnology, and it's based on an assessment of levels of risk and associated levels of containment. So things that produce a very high, that present a very high level of risk of causing disease to others, of causing harm, are permitted to do only in the highest level of containment. And things that that have a de minimis amount of risk are permitted to do in a much looser amount of containment. And then ultimately, it's a decision of agencies such as the FDA and the CDC if something can be allowed out in the general population. So just like it applies to biotechnology, it applies to something as simple as fire. I would say that nothing has caused more harm to human society over the ages of history than has fire. I mean, an atomic bomb is just like a really big amount of fire. Fire bombs, gunfire. I mean, all metals are forged in fire, and metals have made possible all types of weapons and arms. Uncounted millions of people, probably over history, have been intentionally torched in their houses and homes. I mean, just the most horrible things. Yet, on the other hand, without fire, I mean, we would have no society at all. The average life expectancy would be about 19 or 20 years old. We wouldn't have any of the trappings of modern society whatsoever. We'd have no metals and so on. So societies have figured out rules to say, okay, but you can make fire, but you can't start a fire in a movie theater. You can't start a fire in here. No smoking different places, and so on. So we've been able to maximize the benefits and minimize the harms. We've done that with fire. We've done that with radiation. We've done that with recombinant DNA. And I think we will be able to do that with all other technologies. as long as we always keep in mind that we have to act, whatever we do, we have to act lovingly. And by that I mean whatever we do, the happiness of other people has to be essential and part and parcel of anything that we do.
Thank you. Anything else? Yes.
If the FDA wouldn't have approved your daughter's drug, would you have manufactured it outside of the United States?
It probably would. I mean, that's an interesting idea. I can't remember, to tell you the truth, if that went through my head or not. It may have. They probably would not have objected to us manufacturing it. And they wouldn't have objected to us conducting another clinical trial of it. What they would have objected to was of us marketing it and saying that this medicine, is approved for such and such indication. So, I mean, I certainly would have, I think that that's a reasonable thing to analyze. I think a good thing, I'm a huge believer in diversity. So a good thing about having 50 states is that there are different states can try out different rules and regulations. A good thing about having 200 countries is that different countries can try out different regulatory approaches. But I am certain I wouldn't have just thrown in the towel.
Yes.
Hi, I'm an administrator of Boston Children's and also a lawyer. I think, your talk was truly, excuse the pun, breathtaking, and you went through tremendous efforts to bring the drug that you finally did bring to market, really battling a culture at probably all pharmaceutical companies that probably still exists. Given your perspective and the efforts you went through, you made a change at the FDA in terms of their willingness to consider, the P level. Have you been able to make changes in how pharmaceutical companies calculate the benefits of bringing certain drugs to market?
Yeah, it's a very wise question. I haven't, but I'm pretty much 100% convinced that that change is just around the corner, largely as kind of a combined consequence of precision medicine and health economic policy. It gets kind of into you can get into a detailed discussion on this pretty rapidly. But I've made a humble suggestion, and it'll be interesting to see if it goes anywhere, or if variants of it go places. But what I've suggested is one way to bring down healthcare costs, at least in the pharmaceutical side, quite a bit, is for the FDA to, on the one hand, relax the required p-value for demonstrating efficacy from 0.05 to something like 0.1. But on the other hand, to say that if a pharmaceutical company wants to access the 0.1 standard instead of the 0.05 standard, then they have to agree to genomically sequence all patients who go into the clinical trial and then to report the results afterwards, stratified for all genetic polymorphisms that can be detected, along with the results of the trial. If there are statistically significant correlations, then those could then be written on the label to say that this drug is shown to be specifically effective for such and such genomic polymorphism. That would, I think that's going to dovetail with the rapidly dropping cost of genomically sequencing people's genomes. I'm almost certainly convinced within 10 or 15 years, if your physician doesn't have your genome available to her, him, on the cloud, probably should go to a different physician. And third-party suppliers of information, of bioinformatic information, will start associating and providing, probably as a fee for service, pharmacogenomic information showing which gene sequences are particularly associated with a better or worse response, or a worse or more benign side effect profile for different drugs. So drug companies will think, well, if I access this 0.1 p-value, there's a higher likelihood that my drug will be approved. So that's good. I can make half the size of a clinical trial. That's good, less cost. There may be more competition in the market, which will bring down prices. That's good for everybody else. Physicians will actually have better information on prescribing the drug because they'll have the pharmacogenomic information available to them. Physicians will still have the freedom to prescribe a drug off-label, which would then mean to genomic sequences that did not appear to be particularly effective in the clinical trial. That's a fundamental freedom that they'll still have. Payers may take that freedom away by saying that they're only going to pay for the drugs that demonstrate particular pharmacogenomic efficacy. So all those things are beginning to happen that will affect just the change that you're referring to. And I think just the forces of economics and technology are going to force them to occur within the next 10 to 15 years.
Thank you. We're almost out of time. I do want to take you out of this world for a moment because I've read much about you, and I know that you're a fan of what's happening in private space enterprise and orbital sciences as well. You've said you're absolutely convinced that the destiny of humanity is amongst the stars. Can you tell us a little bit about what you see there and in the next 10, 20, 50 years? What's going to happen outside?
Well, first, I only like to make predictions that I'm like virtually certain are correct. And since we're all on a planet in the middle of a galaxy, we've already achieved the destiny of amidst the stars. So whatever we do, we're already amidst the stars, so that's come true. I certainly, I've had like the great honor to live through a period of time when sometimes people were in space, sometimes people weren't in space. Now people are always in space. We kind of take that for granted, but it's been, many years since there have not been people in space. The rate of the number of satellites, people talk about collision threats among satellites. There's so much stuff in space. True to our nature, there's so much junk in space too. So we have, very reputable business people like Elon Musk, the head of Tesla, saying that, they're going to go to develop missions to Mars. Richard Branson, the head of Virgin Atlantic, space tourism to space. So to me, it's just kind of obvious. Humans are, as a species, is the species that move. And it's one of my greatest, most personally passionate causes, frankly, is the cause of migrants. I think it's wrong to prevent people from moving to whatever part of the world they want to move to. Humans moved out of Africa at least 4 different times. It is inherent in our species to move. So as soon as the technology allows us to move off the planet, it's like totally obvious to me we'll do that.
Thank you so much.
Sure, my pleasure.
Thank you.
Thank you so much.